Alright, so today what we're going to do, this is MathStat341, lecture, say 22-ish. We're going to look at sums of random variables and try to get explicit closed form expressions. And this is going to be our beginning of hopefully integrating without integrating, and showing how you can bypass a lot of very tedious technical calculations. I want to try to emphasize as much as possible good ways to look at problems, and sometimes when you have a choice of various things to do, some choices are better than others. So for instance, when you're doing a lot of data analysis, it's often easier to work with powers of 2 than things that are powers of 10, just because of how computers are structured. So let's do sum of 2 uniform 0, 1 independent. So we want to let x be x1 plus x2. Each xi is uniform 0, 1. And if you want, you should have some intuition of what this is, just by considering any game with a die. If you roll a die, you get the numbers 1 through 6 equally likely. If you roll 2, you get the numbers 2 through 12. And you see for 2 die, it's some kind of triangular shape, where the extremes, the 2 and the 12, happen to be 1s. The middle happens 7 out of 36 times. And you might expect some kind of triangle. What can you tell me about x before we even do any of the calculations? What do you know about x?
You can look at the mean
Good.
1.
So the expected value of x is equal to the expected value of x1 plus the expected value of x2, which is just 1/2 plus 1/2, which is 1 x. We could also calculate the standard deviation as well. Great. What else do we know about x?
Well, I guess you mentioned we know like the shape of x roughly.
Well, I said that from Dye's intuition. We haven't proven that.
Okay.
You could say I expect that,
Yeah.
but what do we know must be true about x?
It's between 0 and 2.
Excellent. So we know 0 less than equal to x less than equal to 2. And there's one other nice fact we know about x.
That's probably...
We know it's a probability distribution, but it's similar to something about the triangle. What can you tell me about this distribution? What nice property does it have?
Oh, it's symmetric.
It's symmetric about what point?
1.
Yeah. Symmetric about 1. And let me give you a quick proof. Let's let yi be 1 minus xi, and that's also uniform 0, 1. So if you look at y1 plus y2, this is equal to 2 minus x1 plus x2. I can't tell the difference between y1 plus y2 and x1 plus x2. They're both sums of 2 independent uniform 0, 1 random variables. They must have the same distribution. So it has to be same distribution as x1 plus x2. And what I can deduce from this is I only need to calculate what's going on up to 1, and then I know what's going on from the other part by just looking at 2 minus that. So enough to study big X less than equal to 1. And again, whenever you can make quick calculations like this, you make your life so much easier. As you go further and further, as you add more and more of these uniform random variables, you're going to have more and more things to take care of and to deal with. All right. So let's keep it focused. All right. So let's look at the density of x. So the probability that x is less than equal to little x, we'll take x to be in 0, 1. So we talked about the CDF method, and we used that to get the convolution. So we got the density is equal to the integral minus infinity to infinity, the density of the first one, let's say t, and then the density of the second one, x minus t dt. So we've done this formula many times. And this is the formula for the density of a sum of 2 random variables. If you forget, you can start out by calculating the CDF, and then differentiate past the derivative through the integral sign. Well, because these are uniform random variables, I don't really have to integrate from minus infinity to infinity. This first one, t has to be in 0, 1. Right? If t is not in 0, 1, there's no contribution. And for the second one, we need t to be, we need x minus t to be in 0, 1. So we need t to be in x 1 plus x. Oh, what did I do? Oh, no, I did it wrong. It's x and then x minus 1. So it's x minus 1 x. Sorry. So I want to put t over to the other side. So good. So if t is equal to x minus 1, then I get 1. If t is x, I get 0. And now you can see why we want to break things up based on whether or not x is greater than 1 or less than 1. Because that's going to change how things are here. Since we're assuming x is less than 1, what range do I have to look at for t? Well, I have to do both of these. So it's got to be a subset of 0, 1 from this. It's got to be a subset of x minus 1x from this. So how do those two reinforce each other? What do we get? What can you tell me about x minus 1? What kind of number is that? Since x is less than or equal to 1, x minus 1 is? Either 0 or less. So which wins out, the 0 or the x minus 1?
Oh, the 0.
The 0, right?
Yeah.
I've got to be at least 0.
Oh,
I've got to be at least x minus 1. So because of this, it's got to go 0 is the one that wins. For the other one, I have 1 and x. Which is the smaller one?
X is the smaller.
X is the smaller one. So that's going to be the range that you get. It's going to be from 0 to x. And so now we get that it's the integral from 0 to x. Well, the density is really nice. What's the density? I have a uniform random variable on 0, 1. The density is just 1. If it was a uniform random variable on 0, 2, what would the density be? 1, no.
One half.
1 half. It's on 0, 2. If it was a uniform on 0, 5, it would be 1/5. So I get 1 from the first, 1 from the second, dt. Almost the easiest integral you can do. Right? You know, I'm integrating 1 from 0 to x. This is just x. And so we know the density looks like this, going up to 1. And because of the analysis we did earlier, we know the distribution is symmetric about the point 1, so it's got to come down like this. We could calculate the area under this curve using calculus and prove that the area under this curve is 1, and thus it's a probability distribution. We don't need to because it's a probability distribution, but maybe we did an algebra mistake, so it's not bad to check. Who wants to find the area under this curve by calculus? Who wants to use some other method?
You can use the area of a triangle.
Yeah, area of a triangle. It's 1/2 base times height. The base is 2, the height is 1, the area is 1. Right? Calculus is wonderful, but if I give you a shape like a triangle or a square or a rectangle, thou shalt not use calculus, right? Just calculate it directly. This doesn't prove that we are correct, but it at least shows that our answer is consistent. It does integrate to 1. This is good. To get even more confidence, you could actually take x to be larger than 1 and just go through the calculation and see what you would get. All right, so the hardest part in problems like this is the bounds of integration. Even though it's only a one-dimensional integral, the different density functions here often have different restrictions. And it's best to just go very slow, very methodical. Well, I've got over here, I've got this one and this one. Which one is the one that dominates? Here I need t to be at least 0. Here I need t to be at least x minus 1. The 0 wins. For the other one, I need t to be at most 1. I need t to be at most x. The x wins there. And then, once you have that, I can replace this with 1. Remember, the density is not 1 everywhere. It's only 1 for inputs between 0 and 1. Building on our success, we could now calculate sums of 3 or sums of 4 random variables. If we did the sum of 3 random variables, one thing I could do is I could take my first density to be this, and my second density to be the standard uniform, and just do them together. If I did 4 random variables, I would just take this as my density and convolve it with itself. And this is the advantage of parentheses and grouping, and we've talked about this a lot. If I have x1 plus x2 plus x3 plus x4, if I group it like this, call this x12 and call this one x34. Each one of these we now know is a triangle. So it become a triangle convolved with a triangle. And it's just sometimes more convenient to do powers of 2 because we can keep grouping like this. Now the important thing to note is uniform plus uniform is not uniform. The shape changes. As we keep adding uniforms to uniforms, as long as they're independent, what should it converge to?
Normal.
Normal. So this should hopefully suggest, so uniform plus uniform is not uniform. We know the more uniforms we add, it gets closer and closer to normal. I wonder what happens if I add 2 normals. Anybody know what you get if you do normal plus normal? Normal plus normal is normal. So normal plus normal is normal. This is an example of a stable distribution. It means the shape doesn't change. Now, some of the parameters could change. It's not necessarily the same normal as before. In fact, the variance has to grow. It could be the case that the mean is the same. So let's do sum of 2 normals. Okay, who is looking forward to integrating normals? Okay, so the goal is not to integrate normals. Have I proven to you that the normal integrates to 1 by doing the polar trick? You square the normal integral. Have we done this? We haven't proved that the normal is a proper distribution? Okay. So,
Was it on one of the slides that you showed me?
probably, so I'm going to just do the standard normal. Okay? You can do change of variables if you have a mean. You can do change of variables if you have a standard deviation. I'm going to just do this. The proof is wonderful. It's a math 150 result. So look at the square of the integral. Minus infinity to infinity, 1 over 2 pi e to the negative x squared plus y squared over 2 dx dy. So I've squared the integral and I've combined things. Now I do a change of variables. Dx dy in polar goes to r dr d theta or dr r d theta. This is a little bit better way to view it because I want to make sure I go from area to area. If x and y are in meters, this is meters squared. But dr d theta is not in meters squared. The theta, the radians is unitless. But r theta, the measure of an arc, that is a length. One quick way to see this is if you look at a circle and you look at, pi r plus delta r squared minus pi r squared, you will get 2 pi r delta r for the whole angular ring if I go all the way around. If I only want to take part of it, then if this is delta theta, then the fraction I get is delta theta over 2 pi. So I'll have a plus pi delta r squared times delta theta over 2 pi. The 2 pi cancels there. I'll put an extra 2 down there so I can cancel. This is going to have a delta r, delta theta. This is going to be a third order term that's going to be negligible when you integrate. I'm just quickly reviewing 150. Over here, the 2 pi cancel, you get r, delta theta. And that's your angular measurement. I mean, that's your area measurement for that little wedge. And this is where the r dr d theta comes from in multivariable calculus. I'm not going to reprove the change variable formula, or perhaps prove would be a better word to use than reprove. But it's nice to know where these things come from. And so when we have that, if I now change my variables, I get I squared is the integral theta goes from 0 to 2 pi, r goes from 0 to infinity, that'll give me the whole plane, and I get 1 over 2 pi e to the minus r squared over 2 r dr d theta. Well, I can do the theta integral first. The theta integral is just integrating d theta, there's no theta dependence, so I just get 2 pi. And then I have the r integral, 0 to infinity, e to the minus r squared over 2 r dr. This is just e to the minus r squared over 2, 0 to infinity in opposite order because of the minus sign. And this is why we do the switch. Oh, did not move that piece of paper. This is why we do the switch. Because when we do the switch, we get r dr, so the integration becomes very nice. When I put in I equals 0, I get 1. When I put in infinity, I get 0. So this is 1. So this proves that the square root, 1 over square root of 2 pi, is the correct normalization for the Gaussian. So this is one of the most important integrals there is. This is actually, another way of viewing this is a special value of a Gaussian, which we may see later today, a special value of the gamma function, which we may see later today, depending on how things go. How many of you saw this integral in Calc 3? Okay, no comment while Kim was recording. So this is one of the most important integrals you can do in Calc 3. And it's a wonderful application of why we care about all these different change of variables. This is a surprising problem. I'm giving you this one variable integral, and pi is coming in the normalization factor of the Gaussian. Where is this pi coming from? It's coming from this change of variable. And this is really the good way to look at it. All right. So we at least now know that the standard normal is a probability distribution. You now need to redo this calculation if it has a different mean and if it has a different standard deviation. I will leave those as exercises to you to just do the integration change of variable. This is now just very simple one-dimensional change of variable. Strongly urge you to make sure you can do that. I want to sum two Gaussians. It's really not a big deal if they have different means, because that just translates everything. If one is mean 5 and one is mean 7, screw this. Just make them both have mean 0, and then add 12 to everything at the end, because that's 5 plus 7. So I can handle different means without any trouble, so I'll assume the means is 0. Different standard deviations, however, I have to allow that, because otherwise I'm stuck with assuming that all of my Gaussians have the same standard deviation, and that I don't want to do. So I will assume x1 is normal with mean 0 and variance sigma 1 squared, and x2 is normal with mean 0 and variance sigma 2 squared. We'll let x as before be x1 plus x2. Now we know a lot of things about x. What's the expected value of x?
Expected value of x1 plus x2.
Right, which would be? So they're both normals with mean 0 and variance sigma of 1 squared sigma 2. So it'd be 0. Excellent. And what about the variance of x? What should the variance of x be?
Well, you can just add them.
Yeah, you would just add them. So it would just be sigma 1 squared plus sigma 2 squared because they're independent. How many parameters does a normal have? 2. I've told you its mean. I've told you its variance. So the conjecture is that x is normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. And if true, then as a corollary, if you had x equals, say, x1 plus xn, then x would be normal with mean, in the most general case, mu1 plus mun, sigma 1 squared plus sigma n squared. And the proof would just be the parentheses as before. Just as we did for uniforms, if we know that the sum of two normals is normals, just add x1 and x2, that's a new normal, with variance sigma 1 squared plus sigma 2 squared. Then add x3, and then that'll be another normal with variance sigma 1 squared plus sigma 2 squared plus sigma 3 squared. So as long as we can prove the case of sum of two normals is normal, then we have everything. Okay. So we just have to do that one case. So I deliberately have not looked at any of my notes for this problem because it's a lot of algebra, and it's bad enough that I have to do it once today. To look at it twice is just too much. So we want to do as much of the calculation as possible without doing painful integration. So we know the density of x is going to be the integral from minus infinity to infinity of f x1 of t, f x2 of x minus t dt. All right, so let's start substituting in. So I'm going to pull out a couple of things. We'll have 1 over 2 pi sigma 1 sigma 2. We have the square root of 2 pi twice, and we have a sigma 1 squared square root, so that becomes a sigma 1. The range of t, what is the range of t for this problem?
Negative infinity.
Yeah, negative infinity to infinity. This one is just a Gaussian that can take any value for input. This is also a Gaussian, can take any value for input. So for this one, it's actually easier than the uniform. So t goes from minus infinity to infinity, and then we'll have an e to the negative t squared over 2 sigma 1 squared, e to the negative x minus t squared over 2 sigma 2 squared dt. Okay? So we need to do this integral. Let's play with it a little bit. So if we look at the exponent, it's negative t squared over 2 sigma 1 squared plus x squared minus 2xt plus t squared over 2 sigma 2 squared. Right? So you do not have to write all this down. This should be in the book. It's not just going through line by line by line and figuring out what's the best way to do this. This is a little similar to what we had in the baseball problem. We had two y-balls, and we had 1 over alpha rs, 1 over alpha ra, and then we had this new 1 over alpha that was somehow combined from them. When I'm integrating this, I can pull out anything involving just x. So I can pull out the x squared over 2 sigma squared. So I can pull out e to the negative x squared over 2 sigma 2 squared. And I'm left with, now I'll have t squared over 2 sigma 1 squared minus, I'll do it plus negative 2 xt plus t squared over 2 sigma 2 squared. Right? So now I can write this as negative t minus h squared over a plus ex. This is the old complete the square. Now the question is just how much algebra do we need to do here? At the end of the day, I only need to understand the x dependence. And so what I'm going to try to do is do as little algebra as possible. Okay? So if I have to integrate e to the negative t minus h squared over a, not a problem. I know how to do that. Will this integral have any x dependence? No. Oops, that should be x squared. So what I want to do is I want to complete the square. So how do I complete the square? So I've got, how do we want to do this? Let's say we have 1 over 2 sigma 2, I'm sorry, sigma 1 squared. Then we'll have t squared plus, minus. And now here we have a minus 2. We have a sigma 2 squared double, so I want a sigma 1 squared, so I multiply by sigma 1 squared over sigma 1 squared. So I'll have sigma 1 squared over sigma 2 squared xt. Does everyone agree that that's the first part? Except I dropped the t squared over here. Right? So I really have to be very careful as to what is my coefficient of my t term. So, goodbye. So if we look at this, well, we have a 1 over 2 sigma 1 squared plus a 1 over 2 sigma 2 squared t squared, right? And then minus, we have a 2 xt over sigma 2 squared. That looks good.
Do we not include the 2 as the coefficient for the...
Oh, we do, thank you. Now it looks better. So again, I'm trying to just show you how to do this without actually doing the integration. So we want to complete the square. So let's give this thing a name. Let's call that C. Just so we don't have to keep writing everything again and again and again. So this would be C. You would have t squared minus the 2's cancel. Multiply this by C over C. So we would get xt over C sigma 2 squared, I think. Yes? There's a good chance I'm going to make an algebra mistake, given that I just made one a moment ago. So please be aware and watch. Well, now we just want to complete the square. So this would be C. I can write this as t squared minus xt over C sigma 2 squared plus. So I would want, it's going to be something involving just x, right? 2 square root of C, no, 2, I think C sigma 2 squared.
Well, should be x squared.
And it should be x squared. And then subtract off x squared over 2c sigma 2 squared. So let's look. If I now write this as c t minus x over I think I want,
Would be like, do we want like c squared sigma 2 to the 4th?
fourth, right, that's what I'm saying, because we want to take the square roots of things. I think we want c squared sigma to the 4th. And then we need to get a 1/2. So I think I want to maybe a square root of 2. No. Because what I want is, I want to get something like this, which is going to be twice this over here. So I think I want a square root of 2 down here.
Well, that should be twice the root.
Because now when I do this, if I take x over square root of 2, wait a minute, no. I think we, so I think a better way to do this is write it as, we're going to have x over square root of c, so sigma 2 squared t, do I want to, so here, then we give an x. Because that's what I want. Because now when I multiply this by t, I'll get xt over
So
c.
you want 4 in the denominator.
So I want 4 in the denominator. So this should become a 4 here, this should be a c squared, and this should be a sigma to the 4th.
Yeah.
And now when I multiply this out, if I take x over 2c sigma 2 squared, when I square this, I'll get t squared minus twice xt times this, so the 2's now cancel, plus x squared over 4. So then I have to subtract off the x squared over 4 c squared sigma 2 to the 4th. All right. So now we've completed the square correctly. And so now, when we go back to integrate, we get fx of x. Well, we have a 1 over 2 pi sigma 1 sigma 2. We pulled out an e to the negative x squared over 2 sigma 2 squared. This term can be pulled out of the integration because it has no t dependence. Remember how we're taking negative of the exponent, so this comes out with a negative sign. So the e to the negative x squared over 4 c squared sigma 2 squared. And then we have
Should there be another negative? Because that's also.
oh, sorry. This should be a positive now. Because it was a negative here, a negative, and negative. I told you I'd make algebra mistakes. So this becomes a positive. And then we have the integral t goes from minus infinity to infinity. E to the negative c t minus x over 2c sigma 2 squared squared. dt. Okay. I'm not even sure if it's still fitting on the camera. Okay, it's getting bad. But life is good. We're done. And we're not done just because we're frustrated we don't want to deal with this anymore. We are done because we are done. This is a number, right? This is just some number. So at the end of the day, you get it's some constant times e to the negative, say, alpha x squared. Right? If you look, all the x dependence is as an x squared. And you can see that this is clearly going to be larger than this term, so it will be negative. This has to be a Gaussian. So because it has to be a Gaussian, we know the variance. This implies that alpha has to be 1 over 2 sigma 1 squared plus sigma 2 squared. And it implies the constant has to be 1 over the square root of 2 pi sigma 1 squared plus sigma 2 squared. Done. As a good exercise, go through and see how badly I did the algebra and see where's the errors. This is why I wasn't too concerned because I knew where this was going and I knew I wasn't going to finish the integration. This is the power of the theory of normalization constants. Because it's a probability distribution and it integrates to 1, once I know the functional form, I can figure out what everything else is. What I needed to know is I needed to know what the variance was. Well, I know what the variance is. It's independence. Sigma 1 squared plus sigma 2 squared. That tells me exactly what this is. And you could play some games and hopefully everything will work out. If we had more time, I would go through and do that algebra. I'll leave that as an exercise. But because we were able to identify the approximate shape, that we can then refine that guess and get exactly what's going on. This is wonderful. And so now that I know it has to look like this, the only thing for alpha is this, and the only thing for constant is that.
So basically, if you want us to show like the sum of those two
Is a
like,
Gaussian.
is a Gaussian, then like we can say like at this point,
Yes.
because of the functional,
Yes.
and we don't have to do that.
Correct, because we now know that this has to be a Gaussian. And there is a relationship between the constant and alpha. So you could actually go through and collect what the sigmas are here. You could figure out exactly what this is in terms of c. The fact that we have the negative x, that's no problem. We can just translate t and that drops off immediately. So that part's not bad. But then you would have to integrate this and you would start to say, oh crap, right? It's negative c t squared. We did negative x squared over 2. So I have to convert from c to that. And this is the same then as a Gaussian, where the variance, so I want C to equal 1 over 2 sigma squared. So that means sigma is equal to 1 over 2c with a square root. So this integral here, if I had a 1 over square root of 2 pi sigma squared would be 1. So this is going to just equal the square root of 2 pi sigma squared, where sigma squared is 1 over 2c. Yes?
How do you know you don't actually normalize?
Because we are summing two independent random variables. That's also a random variable. It has to integrate to 1. That's the whole key behind all of this. This is integrating without integrating. I don't actually have to do this. I don't have to keep track of what everything is. I could. And this is why originally, I only need to know enough to figure out what is this term here. So again, I may have done an algebra mistake. I hope not. It doesn't really matter. And now we know that the sum of two normals is normal. Most random variables are not going to have this property. So this is called being stable. So if you are equal, if you have the same shape, there's not that many distributions that are stable. Another one is the Cauchy. I don't think we've done the Cauchy in class yet. So the Cauchy is one of my favorites. So f of x is 1 over 1 plus x squared, and then you need a 1 over pi for the normalization constant. You could replace the x with x over a, and then have a family of Cauchys. Now, this is not really a nice distribution. And the reason it's not nice is it doesn't have a mean and it doesn't have a standard deviation. Now you might say, what do you mean it doesn't have a mean? If I integrate, f of x dx, this is 0 because it's an odd function. Well, this is where you need to do some advanced integration theory. If you have an indefinite integral, then you want the absolute value of the integrand to be finite in order to make a claim like this. And the problem is the integral will give you different values depending on how you go to infinity. So for example, if I look at this as the limit as a goes to infinity from minus a to a of x, f of x dx, that is 0, because it's an odd function on a finite interval. If I look at it as the limit as a goes to 0 from minus a to twice a of x, f of x dx, this is the same as the limit as a goes to infinity, the integral from a to 2a of x 1 over pi 1 over 1 plus x squared dx. Well, when x is really large, x over 1 plus x squared is approximately 1 over x. So this is approximately the limit as a goes to infinity, 1 over pi, the integral from a to 2a, 1 over x dx. What function has derivative 1 over x? Log. So this becomes the log of 2a minus the log of a, which is the log of 2. So this is basically the log of 2 over pi. So unfortunately, this function does not have a mean. It depends how you go to infinity. That said, if you want to say, come on, Professor Miller, let's just always go to infinity symmetrically. We're among friends. We're not going to be theoretical mathematicians. Let's just use this. Okay. I'm willing to grant you that it has 0 mean. Definitely has 0 median. If you try to calculate the variance, you would need an x squared. And you would have x squared over 1 plus x squared. As x gets large, what does x squared over 1 plus x squared look like? It looks like 1. So it has infinite variance. So even if you're willing to accept the fact that it has 0 mean, you're screwed when you get to the variance. It has infinite variance. This is a terrific example of a distribution when you want to test just how much do you really need certain assumptions. This distribution has no moments. Yes?
So if I was like, undefined mean and infinite variance, like, is it,
It's
like,
still a
useful?
probability
Like,
distribution,
is-
yes.
Is it like
Yes,
used in
absolutely.
Okay.
And if you look at the additional comments, I have a lot of stuff about the fractal misbehavior of markets, where Mandelbrot applied fractal geometry to study the markets. And he has a beautiful series of papers with some colleagues where they actually look and they say this idea of this random walk on Wall Street and flipping a coin does not do a good job of modeling the stock market. It does not have enough days of large deviations. And things like the Cauchy distribution does a much better job of describing reality. And in fact, you can put the Gaussian and the Cauchy into a big superfamily where they're both extreme cases. So there's a lot of wonderful connections between them. So the only thing we haven't done is shown that this actually integrates to 1. Now the fact that I give you 1 over pi, 1 plus x squared, well, we know this function is decaying rapidly. So the function will definitely be integrable. The question is, why is the normalization constant 1 over pi? And so, I'll list this. Does anybody know what the derivative of arctangent of x is?
Is that 1 over 1?
Yes! Excellent. It's 1 over 1 plus x squared. So, what is the tangent of the arctangent of x? X, right? I take the tangent of the angle whose tangent is x. I get x. So by the chain rule, tangent prime at arctangent of x times arctangent prime of x equals 1. So arctangent prime of x is 1 over tangent prime at arctangent. All right, what's the derivative of tangent?
So 1 minus x.
So tangent is sine over cosine. So if you use the chain rule, I think you get the derivative of tangent is 1 over cosine squared. So this is going to just be cosine squared of arctangent of x. All right, let's draw a triangle. Here is arctangent of x. So if I choose this to be x and this to be 1, then here is a triangle where this is the tangent of this angle is going to be x. What's the hypotenuse going to be? Hypotenuse.
Root of x squared plus 1.
1 plus x squared. Right? We always put the 1 before x squared. So, what's the cosine of arctangent of x? Well, cosine is adjacent over hypotenuse. So it's 1 over the square root of 1 plus x squared. And since we square it, then we get arctangent prime is 1 over 1 plus x squared. Oh, battery is low. Interesting. I've never had that happen before. Okay. So let's quickly finish the problem. So let's integrate from 0 to infinity of 1 over 1 plus x squared dx. This is equal to arctangent of infinity minus arctangent of 0. What angle has an arctangent of 0? I'm sorry, what angle has a tangent of 0?
0.
0. What angle has a tangent of infinity?
When cosine.
So the horizontal part is 0.
Cosine is 0.
So what angle has a tangent of infinity? Pi over 2, because we always do these in radians. So if we integrate from 0 to infinity, we get pi halves. So if we go from negative infinity to infinity, we just have to double things by symmetry. And there's the normalization constant for Cauchy. The normalization constant is just going to be pi. All right. We have 5 minutes of, we've talked about the gamma function a little bit in this class already, right? All right, so since we've mentioned that, and since we've just done Cauchy here, I will do a fast, fun application of this function. It'll allow me to review the geometric series formula, which you've seen. We do not have much time, so I'm not going to worry about doing things rigorously. Let's integrate from 0 to 1 of 1 over 1 plus x squared. So this is arctangent of 1 minus arctangent of 0, which is what? What's the arctangent of 1? What angle has a tangent of 1? Pi over 4. This is the same as the integral from 0 to 1, 1 over 1 minus negative x squared dx. Because I'm writing it as 1 minus negative x squared, what does this remind you of? Okay, and where have we seen that before? Sometimes we don't use the letter x, we use a different letter. If I use the letter r here, 1 over 1 minus r, what would that remind you of? 1 over 1 minus r is 1 plus r squared plus r cubed plus da da da. Right? So this is the same as the integral from 0 to 1, the sum, and it goes from 0 to infinity of negative x squared to the n dx. Technically, what I should do is I should integrate to 1 minus epsilon and take the limit as epsilon goes to 0. I don't want to do that. I want to play fast and loose with the mathematics. I'm going to switch the order of sums and integrals because I want to. I go n goes from 0 to infinity. I'll have a negative 1 to the n, integral from 0 to 1 of x to the 2n dx. X to the 2n, that's easy to integrate. It's x to the 2n plus 1 over 2n plus 1. So this is going to be a sum, n goes from 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 at 0 and 1. So the only term that survives is x equals 1. So you get 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th. And this is pi over 4. So here is a series expansion for pi over 4. This is called the Gregory-Leibnitz formula. And in fact, not only does it give you an expansion for pi over 4, you can actually tell how close you are. If I stop over here at the minus 1/3, did I overestimate or underestimate? Under, because 1/5 minus 1/7 is positive. 1/9 minus 1/11 is positive. If I stop after a negative term, I underestimate. If I stop after a positive term, I overestimate. So if you want to get pi to a given tolerance, here is one way to do it. It's not the best way by any stretch, but it's at least one way to do it. So we saw a lot today. In the next class, we will go and we'll start doing more with the gamma function. But the Cauchy distribution should be added to your list of just distributions that you know. And the reason you should know it is because it's so bad. It doesn't have a mean. It doesn't have a variance. Is your theory strong enough to handle things like the Cauchy distribution? If not, what do you need to be able to say something? What kind of constraints do we need on our random variables to be able to get a theory? Do we expect sums of Cauchy random variables to converge to a normal? So I'll end the class with this. Yes?
So in terms of homework, that's still on Monday, correct?
Yes.
Okay. Sorry.
Right. Yeah. There was no homework due today.
I mean, yeah.
So for sums, I said Cauchy is also a stable distribution. So sums of Cauchy is Cauchy. Can that converge to a normal? No. So it's not the case that sums of independent random variables always converge to a normal. Here's the simple proof. Now, the nicest way I know how to prove that the sum of Cauchy is Cauchy is to actually use complex analysis. And this is a great adage. Sometimes the shortest proof to a theorem in real analysis is to detour through the complex plane.
Wait, then does that mean the central limit there doesn't hold for Cauchy?
Yes. So ask yourself, what are your conditions for the central limit theorem? Ah, yes. And so that's the whole point of this exercise. And there is a thing that works when the central limit fails. There is the median theorem, which is not emphasized nearly enough. The median exists for the Cauchy, and the distribution of the median of sums of Cauchy converges to being normally distributed.